Hello all keen learners. As you know that how meticulous we are for learning this subject. So today is the second numerical on limitations of Euler's formula. So first understand this numerical. A 50 mm by 100 mm timber. See this 50 mm is width and 100 mm is depth of the timber is used as a column with fixed ends. So boundary conditions are both end of fixed of that column. Determine the minimum length at which Euler's formula can be used. So this is to find C, determine minimum length and at which Euler's formula can be used. So this is important wording. And E, modulus of elasticity, they are given us 10 GPa and crushing stress sigma C is 30 MPa. And what central load can be carried with factor of safety 2? Central load can be carrying with factor of safety 2. Central load we will find by using that crippling load formula pi square EI by L square. And if the length is 2.5 meter, that means that central load and in another sense crippling load we will find for that 2.5 meter length. So solving methodology of this numerical is first understand solving methodology, and before that understand this problem statement. Minimum length and central load, and minimum length we will find that Euler's formula can be applicable. So for that, see, with the help of this formula LE by K is greater than equal to, this is limitations of Euler's formula, pi square E by sigma C. With the help of this formula, this LE, what is this LE? See, the boundary conditions they had given us in numerical. Boundary conditions, both ends are fixed. So both ends are fixed, that means effective length is equal to actual length by 2. So put in this formula, LE is equal to L by 2. So that means LE is L by 2 into K. So we will find this L like that way. See, we have E, we have sigma C, and K we will find by using K is equal to under root of moment of inertia upon K is equal to under root of I upon A, moment of inertia upon area. Moment of inertia of that rectangle and area of that rectangle. So that way we will find this minimum length. Now second is central load, and central load can be carried with factor of safety 2 and effective length is 2.5 meter. See, central load, I told you central load, that means that which that that formula P, buckling load formula PCR is equal to pi square EI upon L square. So this formula is, we know that pi square is constant, E is, we have E, we have I, and we have L square. So by that way we will find this PCR, and this PCR, divide this PCR by factor of safety, we will find safe load. So let's solve this numerical. Apply reverse engineering for solving that type of numericals. Reverse engineering, that means first understand numerical, then understand problem statement, then understand directly which formula is applicable to solving that numerical, and know that what are the things required for solving that formula. Like reverse solving is very good thing. So see how to solve it. our problem statement is minimum length, and we know that for that minimum length this LE upon K is greater than equal to pi square EI upon LE square. EI upon not LE, sigma C square, crushing strength square. Okay, this is wrong. Pi square E upon sigma C only, because see this PC formula is this pi square EI upon LE square, and remember that this is different. This is pi square E, I is not here, and this is sigma C, not square of that sigma C, so remember that. So this is limitation of this Euler's formula. LE upon K is greater than equal to, LE upon K should be greater than equal to under root of pi square E upon sigma C. So this LE, how to find this LE? First read this numerical. Boundary conditions are here, somewhere they had given us with fixed end. So column both ends are fixed. That means buckling is like that. And we know that effective length is nothing but the distance between point of contrapicture. So, and this is actual length. Actual length denoted as L, and this distance between point of contrapicture is effective length. So, effective length is equal to actual length by 2. We had seen it in our previous lectures, actual length by 2. And actual length here is, they had given us the actual length. No, they don't give us actual length. So just put this L is equal to L by 2 in this formula, and see here our problem statement is minimum length minimum length solving. So L by 2K greater than equal to pi square E by sigma C. So see, our problem statement is this L, because we don't know this L. See, in this numerical they had given us length, but this length they had given us for solving this central load only, and another problem statement is minimum load. So for that we are solving this minimum length. So we know that E, we know that sigma C, we know that pi, we don't know this K. So solve this K now. But K is equal to radius of gyration is equal to under root of moment of inertia upon area. And see, our shape of that column is like that rectangle. This side is 50 mm, width breadth is 50 mm, and depth is 100 mm. So calculate moment of inertia, and remember that this is rectangle shape. So, and see, we are in, we are always interested to put least moment of inertia while calculation of like that. So always remember that least moment of inertia, that means this axis passing to minimum length of this rectangle. Minimum length is 50 mm, so pass that axis through like that. This is y, consider this as y axis. So IYY is equal to, so parallel side is 100 mm, so 100 as it is, multiply by this 50 cube divided by 12. So this IYY is this is least moment of inertia. So IYY is 10.4166 into 10 raised to 1.0416 into 10 raised to 6. So 1.0416, that means 1.042 into 10 raised to 6, and you know unit is mm raised to 4. So like that way calculate it. What I told you, that we had considered least moment of inertia, and least moment of inertia always passing through that minimum length axis. Remember that. I is 1.042 into 10 raised to 6 divided by, now area is simple, 50 into 100, area of rectangle, it is 5000. So this K is 1.042 into 10 raised to 6 divided by 5000, and root of that, it is 14.43 mm. Remember, unit of radius of gyration. So put this K in that equation 1, E and sigma C also, you will get that L. So equation 1 becomes L as it is 2 multiplied by K is 14.43 mm pi square. E is given quantity, modulus of elasticity, 10 into 10 raised to 3 MPa, divided by sigma C is also given quantity, crushing stress, 30 into 10 raised to 3. So this L. See, this is greater than equal to. So use it as equal to and solve it. So calculation, pi square multiplied by 10 multiplied by 10 raised to 3 divided by 30 into 10 raised to 3, it is 1.8137 multiplied by 2 into 14.43. So it is wait, this 30 MPa. See, this 30 is in MPa, and why we write here 30 into 10 raised to 3 MPa upon. So this is mistake. Never make this mistake. See how mistakes happens. Learn from mistakes. MPa, MPa. This is not like that. This is correct. GPa into MPa. So this is only 30 MPa. Pi square into 10 into 10 raised to 3 divided by 30 into 2 into 14.43. It is 1655.33. So our first objective is complete. Unit is mm. So this is minimum length at which Euler's formula can be used. So by using that limitations of Euler's formula, we had find this length. And see, recheck that unit of that length. This 10 into 10 raised to 3 is E, so unit is Newton per mm square. This unit, MPa, that means Newton per mm square. 1 MPa is equal to 1 Newton per mm square. And this K is mm. So this get cancelled, this mm is remaining. So yes, unit is correct. Now we will go towards our second objective. Second objective is finding central load. So how to find central load? Central load, that means that central load is nothing but that buckling load formula. PC is equal to pi square EI upon LE square. So we know pi square is constant, E is given quantity, 10 into 10 raised to 3 GPa modulus of elasticity. I is least moment of inertia. Always use least moment of inertia while calculation of load for safer side calculation. So where is I moment of inertia, C, 1.042 into 10 raised to 6. Divided by L square. L, what is L? Effective length. See here, L is L by 2, and we had find this. L is 1655.33. So 1655.33 by 2 square. Now calculate this with the help of calci. Engineering calci, pi square 10 into 10 raised to 3 multiply by 1.042 into 10 raised to 6 divided by 1655.33 divided by 2, square of that. Wait, we had make mistakes again. See, understanding question, if the length is 2.5 meter, this is also important, not for that minimum length, for that 2.5 meter length, this question is interested. So right here 2500. Square into 10 into 10 raised to 3 into 1.042 into 10 raised to 6 divided by 2500 by 2 square. So it is 65.82 into 10 raised to 3, and unit is Newton. Why unit is Newton? Because this is in Newton per mm square, this is in mm raised to 4, this is in mm square. So here mm square remaining, so this is Newton is remaining, so that's why it is in Newton. See how mistakes are happening and learn from that mistakes. So 16.82, this is 16 or 65, 65.82. 65.82 into 10 raised to 3 Newton, and in kilonewton it is 65.82 kilonewton. So this is crippling load or buckling load. Now shape load, PS is equal to PC upon factor of safety, and factor of safety is 2. So 65.82 divided by 2. So shape load for that fixed rectangular column is 65.82 divided by 2. It is 32.91 kilonewton. this is safe load. For that, 2500 mm length fixed rectangular column, and see, this is timber column, and minimum length that Euler's formula should be applicable is 1655.33 mm. So by that way we had solved this numerical. So thank you very much.